Well, welcome all of you to our workshop today. My name is Jules Damji. I'm not going to introduce myself again after this elaborate, comical one. And my co-presenter, Archit, we are here from Anyscale. And just before we talk about what we are here today and why we are here, just want to get an idea how many of you have heard about Ray? Okay, you can leave now if you want. Have you worked with Ray at all? Okay, brilliant. Nice to know. We should probably give them stickers, right? Okay, I do have some stickers, so you'll actually get some more of your stickers. Before I'm not going to go through this because Dimitri has done a fabulous job, and my co-partner over here. So who we are and what do we do? So we work for a company called Anyscale. We were the original creators of Ray. And Ray is a distributed framework that was developed at Rice Lab, which is the research lab here not here, but in California in UC Berkeley. Sort of a crucible of innovation. A lot of really good projects actually came out of there. Before that, it used to be MLflow, where Spark came out, Mesos, Cafe. So it has the pedigree of creating some of the most innovative and disruptive technologies from UC Berkeley. And Anyscale is a company which provides the managed service for you to be able to actually scale your workloads at massive scale. So Anyscale is a company that actually supports the open source version of it. And what is our mission? It's a very simple thing. We want to make sure that distributed computing is simple for everyone in this particular room, no matter your background. You don't have to be a PhD to understand distributed computer system. You can actually use the APIs that we actually provide you to do that. So that's our sort of goal and mission. And so what is the agenda today? What we have done is we have created this particular module. This is normally a 4 or 8 hour course, but we have tried to condense it in 2 hours. It's kind of mind of we have made it sort of introductory as well as intermediate, so that we can cater it and bring it down into the amount of time that we have. We have this room from 3 to 4:30. I'm told there's nobody after here, so I'm going to keep you captive for another half an hour if you want to. You guys can leave at 4:30 if you get tired of, or if you're cured to insomnia, so that'll be fine. So we divided into 2 modules. I'm going to cover the first one, and then Archie is going to give the tutorial on Ray. And what I want to do is I want to start with 20,000 feet. Why? What is the motivation behind Ray? And then go down to about 1,000 feet, talk about Ray architecture and its ecosystems. And then we'll get into the APIs, which will at the 0 feet sea level, and then we'll do some tutorials. Now, I had sent out a URL to set up your machines beforehand, and it's actually completely openish, because if you try to do it right now, you're going to bring the network down. I've been having a lot of problems, so I wouldn't advise you to do install right now. Just follow along. And the exercises that we have at the end of the tutorial are optional. You don't have to do it, because we don't have enough time to do it. But I recommend that when you go home, try to do them, because once you do git clone of that particular Git repository, you will have all the notebooks along with the solutions, so you can actually do that at your leisure. Okay, so why Ray? Why are you here? And I want to start with the motivation behind why the original creators of Ray were looking at why we actually need this particular distributed system. And I think there were 3 industry trends which are actually happening about in 2016 or 17, at the time when the original creators, Robert Nishira, Philip Morris, and Dr. Johan Stoica, who was the director of Rice Lab and also the co-founder of Databricks, the company I worked for 6 years, were looking at the trend that were actually happening. And obviously it was quite clear. Is that from me? It was quite clear that machine learning has become pervasive in every domain. You heard today what Tommy was talking about 1960 when they were doing MLOps with those massive wires to what we are actually today. Machine learning engineering has pervaded each and every domain of the industry. And as a result of that, what's actually happened is that distributed computing machine now is a necessity. It's not an exception. It used to be an exception 5 or 10 years ago where everybody sort of had to be very expert in distributed computing to write one of the first applications. But because of these machine learning models, which are getting large and demand a lot of compute power, distributed machine learning is a necessity, and it'll be a necessity for a long time to come. And obviously, Python is a default language for that. So if you're creating a framework, you have to think about Python. You have to think about the Python ecosystem. So those were the three trends which were actually happening at that time. And today, if you look at the way people are actually scaling the machine learning models, the people who are actually building large foundational models, they require a fair amount of compute demand. They require a fair amount of petaflops. And there is this exponential linear demand of what the computer models actually require along the time. And you can actually see that the CPU just does not meet the demand, right? The demand is so much that the supply is not enough for us to scale at the level that we actually want. And you might say, well, Jill, what about GPUs? You know, we have had these hardware accelerators for a long time. What about the GPUs? GPUs do that, but they don't still meet the demand. You know, what about TPUs? The same thing, right? There is a certain fulfillment, but it doesn't really fulfill the gap that you actually need that. So we argue, we contend, the only way you can actually meet this particular demand if you actually horizontally scale across, right? You just have to scale your training, you have to scale your application, whatever it is, across a large cluster. And the only way is to actually go and distribute. So that's the second trend. People are actually beginning to see that, and that was one of the motivation principles behind Ray. And the final one is that this is inevitably and indisputable, right? Today, you have to, if you are in the ML space, you've got this massive Python ecosystem that has developed over a period of years. And most of the data scientists and most of the ML engineers work on this particular thing. If you are a machine learning engineer who's doing deep learning programming, if you're building any of those, all of these have Python bindings. So Python was and is still the de facto language and continue to be there for a long time. Even the underlying infrastructure might be written in Rust or it might be written in C++, but you have the Python bindings to it. So that's number three, right? So those were the three sort of primary industry motivations that led to the creation of Ray. And so the next step, obviously, going down a little further, is what is Ray, right? What is about Ray? And you can think of it as it's a simple sort of general purpose library for writing distributed computing. And I want you to pay attention to that because I'm going to expound on that momentarily. It's a general purpose because it's not built on any particular framework. If you look at the previous distributed systems, say like Spark, or say like Dask or Hadoop, it was based on some data structure, right? You actually had a Hadoop file system on which you actually did your computation. On Spark, you had a data frame which was actually distributed. You had data sets in RDD and data frames now, because it started with RDDs. It's a distributed framework. You actually have APIs that run on top of it. If you look at Dask, similarly, you actually have a Dask data frame. You have bags on which you actually do your iterations or you do your computations. But this is the general purpose that we don't provide you a frame, we don't provide you a data abstraction, but what we provide you is a simple primitives for which you can actually use to build things on top of that. So that's, the other thing is that it's an ecosystem native libraries which are built on top of the framework to scale your machine learning models. And we'll look at it more in depth. And the beauty about it is that this runs on a laptop, right? Today you're going to run Ray on your laptop. You can run it on a public cloud. You can run it on Kubernetes, or you can run it on-premise, wherever you actually want. There is a flexibility of that. You're not bound, you're not beholden to any particular underlying compute infrastructure that you need. So if I were to articulate what is Ray today, I would say it's a layered cake of functionality and capabilities that allow you to scale your ML workloads. And I think it's the important part. The important part is a layered cake. And let's look at what I mean by the layered cake. At the bottom, you actually have your compute infrastructure that actually can run anywhere, right? So you can have Ray run on any of the public clouds which are actually supported today, including your laptop. And at the bottom, which is really the core, is where we actually provide you the general purpose framework that has primitives that allow you to write distributed applications. So these are the APIs that we're going to share with you today. You write those distributed applications, and you don't have to reason about, is it going to be fault tolerant? Do I have to worry about scheduling? Do I have to worry about resources or scaling automatically? You don't have to worry about it. You don't have to reason about it. Ray will take care of it. We'll give you the primitives so you can actually write distributed applications very easily. And then on top of that, as I say, this layer cake, you have the native libraries that are built on top of Ray using those primitive abstractions that I will introduce you today to scale those workloads that you actually need. And in the middle, you have all these integration libraries that work very closely with Ray. So you can actually run PyTorch, you can run scikit-learn, you can XGBoost. All these are integrated with that. And they use Ray as the compute strata to scale your applications. And then finally, if you don't care about any of the two things on the left-hand side, if you are a Python application programmer who just wants to scale up your computations, or if you just want to write a library, you can use those primitives to do that. Hence, the descriptions about it's a layered cake of functionality, and where you are and what you want to do depends on what side of the square you are in. So that's essentially the ethos of Ray is the core that provides you the primitive abstraction, so you don't have to reason about the scaling and all that. You don't have to, where am I going to create a socket, or where is my head node running, or things of that sort. All that is taken care of you. And then finally, the rich ecosystem that we actually have that gives you the ability to use any of these libraries. So in other words, it's a la carte, it's not all or one. You just don't, you can use one, whatever you want to do. If you want to use reinforcement learning to build your agents, then you just use reinforcement learning. Now, if you're using reinforcement learning, then obviously you might be tuning some things, right? You might have your PPO model, or you might have your multi-bandit models that actually wants to tune. And if you want to tune it, you can actually use the hyperparameter tuning. And if you want to train your model, obviously you can use ray train, but it doesn't force you to. You can actually use one or the other. You can use a combination of both. And then if you actually want to do any pre-processing of data for your last mile ingestion, we actually have a thing called data sets, which is not in GA, right? And it's still in beta? Right. It is still in beta. And then, the modern pandas is the one on Ray. You can use Mars, you can use Dask on Ray, you can use Spark on Ray as well. So these are the ecosystem libraries that come straight out of the box with Ray. And then you can write anything. Think of yourself on the far right corner if you actually want your write libraries. Who's using it? Why are they using it? All these companies who actually build things at scale are using all these particular libraries to scale their workloads for the requirements they have. Amazon is using Dask on Ray to do all the pre-processing for their distributed training. Uber is doing all that for their machine learning models. Visa, Wildlife is building Ray Serve to do that. Shopify, Alibaba has actually used these Ray to build their ML platform. So these are some notable companies, and many of them are actually adopting at massive scale. So those are the companies who are actually using it. So what I'm going to do now that I've actually given you sort of a high-level picture, I'm going to get into a little behind the scenes, re-architecture and components. But before I go there, any questions? Okay, brilliant. Nothing much there. Okay, so if you look at the anatomy of a Ray cluster, it's no different from the ones that you might be used to it, right? If you're looking at Spark, or if you're looking at Dask, or if you're looking at Hadoop, it's very similar. You actually have a head node where you actually have some worker nodes which are running, and then the worker nodes, and then you have these nodes over the cluster. The distinguishing characteristic is that on the head node, by convention, you actually have a driver that's sort of scheduling things and talking to the Raylets. Each and every node actually has a process called Raylet, which is a C++ process, and got two threads on it, right? One is a scheduler, and one is an object store. And each worker node actually has the same thing. And they talk to each other, right? So the scheduler, or the scheduler, wherever you come from, it actually sort of talks to each other, and then the object store is your distributed object store built on top of Apache Plasma. And then we actually have a global store, which conventionally right now runs on the head node, and it sort of communicates and maintains the state of who's running what, where, what resources have been consumed, and it gets all that information from the general store where I know that I have a worker node 1 that's got 4 GPUs, so if I have to schedule a particular job, I'm going to do that. The good thing or the unique part about Ray is that it's a distributed scheduler. Like, unlike other distributed systems, you only have a central scheduler that you actually go through, and it fans out the jobs. Over here, a Raylet can actually schedule any particular job from anywhere. So you don't have a bottleneck of going to the central part. So that's sort of together, this creates a global store where you actually have your data stored across the entire cluster, and you have a scheduler that actually knows about who's running where and what the resources are, and you can actually schedule your job accordingly where the demands require for your workload. If I go one level deeper, this is what sort of it looks like. You got the node. Every worker is tied to a core. So if you have 12 cores running on a node, or if you have 24 cores running on a node, you'll have 24 worker processes, and each will be dedicated to a particular core. And then the raylet is the one that actually communicates to all the other raylets to figure out where I can actually schedule things. And the global store is where all the metadata, all the system metadata is run. So only all your functions, all your actors, all the GPU resources, who's running where is actually stored or in the global meta store, and then you broadcast that across to the raylet. So each and every raylet knows, oh, this guy actually is running this particular thing. I can actually schedule something over there because I know it has the GPUs. So that's sort of the whirlwind of where we are. Now I want to go down a little bit further in the Ray distributed design APIs. Now, those of you who come from the software engineering background, you probably heard about design patterns. Can somebody tell me what a design pattern is? Give me an example of a design pattern. Iterator, coroutine, singleton. These are all the design patterns. These were introduced by this Gang of Four book that was introduced that allowed people to have the design patterns. And what design patterns allows you to do is to use a particular a data structure or part of the language in a manner that is either Pythonic or it's Java-centric or Scala or functional programming. These are sort of design patterns. So you have singletons, you have coroutines, you have context managers. These are all design patterns that force and nudge you to use the language in the manner that it should be used, which is more efficient. No different from a speech language that has parts of speech, and a sentence is structured by a verb, and grammar, preposition, all that. No different over here. So Ray introduces three design patterns. One is called a parallel task, which are functions that can be converted into a stateless task. And this allows us to distribute at massive scale. The second one is the Ray objects or features. These are objects which are actually stored in the object store I told you about. And these are features, which means that when you execute a particular task running on a particular node, it might create an object or it might not create an object. And if you create an object and it returns an object, that object is not the value of the task, but it's actually a feature that you can actually query and inquire later on down the pipe. So is this particular job done? So those are what the features. And those of you who come from C++, or those who come from Python, you probably heard about those. And then finally, you have Ray actors. And actors are stateful services that allow you to deploy your stateful service on the cluster. You can use that for messaging or however you actually would. So these are the three design patterns, and they're used across the Ray native libraries very much. Ray actors are the predominantly used for all the libraries, and you'll see what those are. So those are sort of the design patterns. And obviously, those are just the three ones that we're going to talk about today. But there are all these links over here that you can actually do that. By the way, the slides are on the GitHub, on the directory called slides. If you want to follow along, you'll be able to do that. So those are the design patterns. So what did it look like? What do I mean by design patterns? So you can take any particular function, which is a class, and by just adding the decorator called .remote, you can convert that function into a distributed setting by just doing that. Very simple, right? Without the Ray remoter, it's just an iterative function or imperative function that reads a particular file, then does some computation and returns it. Again, add is a function that actually takes two arguments. And those two arguments could be anything, right? It could be a feature, reference to a feature, or it could just be the actual value. And when you invoke that particular function, you just denote that or use a signature called read.remote, and you pass the file one. Read.remote, you file path, and it returns immediately. Right? You just get the reference, the feature back right away. And then you can actually send those references, features, to another function which will resolve at the time when it's actually done. And then when the final result is returned, you actually do a blocking call called ray.get with that particular feature, and that's a blocking call. It'll just wait for the process to finish, and you'll get the result back. If you want to take a class, that you actually have a Python class today, and you want to convert that into a stateful service to maintain the state, all you do is decorate that with, and you can provide any resources that you want. So if you want to make sure that this particular actor is connected or runs on a core that actually has GPU, then you can provide, I want this to be reserved for 2 GPUs. So it'll be scheduled on a particular node that has that particular requirement. And you can also supply runtime environments over here. Let's say that this particular class requires a certain packages. You can actually do that by just sending an argument called runtime environment. That Archit actually works quite a bit on it. And it will just introduce or temporarily install those packages for you. And the way you instantiate an instance of the particular class, you just say counter.remote. Now you got a handle. And once you actually handle, you just invoke just like any class method. But the only difference over here is that you supply the .remote, and then you pass the arguments, and it returns you back, again, a feature which you can actually then do a get on it. So if you translate that into how it actually happens behind the scenes, you got a read array, which could be scheduled on node 1, right? Then just returns the ID right away. The second one could be actually on a node 2. Doesn't matter where it is. If there's data locality, then it'll be scheduled on that one. It returns an inference right away. These are sort of dynamic graphs computed imperatively, eagerly, rather than statically. And when you do a .remote, this could be on a node 3 where the add function is there, and it will get a copy of the references, and then it does a compute and it returns you back. And when you do a get, that's your graph being executed across the cluster right away, right? The reason this is done eagerly, because in machine learning, sometimes when you're doing hyperparameter tuning, you don't want something to statically do that, because you want those parameters to be computed right away so that they can be forwarded to the next parameter server, so the gradients are computed in an eagerly fashion rather than waiting for everything to finish and then you do a static execute. So that's sort of in a nutshell 3 simple APIs. You can take a function, convert it into a task. You can take a class, convert that into a stateful service. And then you can actually use objects to store things in a distributed immutable object store. So here is a diagram of the worker nodes. Each worker node has a shared memory, which is, you can configure how big it is. It's a plasma store based on Apache Plasma, so it's very, very efficient. And any worker process on which a particular function is scheduled, if it actually creates an object, it's responsible to manage its metadata, and it's going to store that in the object store. Now, because these are running shared memory, if I have another process on that particular worker node that needs that particular data, I don't have to do the copy, right? I can just do a 0 copy because it's using shared memory. So there's a very fast, efficient way to share data within the nodes. If I have 20 workers and they all need this particular data, they can get directly from shared memory by using 0 copy, because I don't have to copy that. There's no IPC involved in it. And then if the shared memory gets overloaded, we can always spill that on the disk. So how does this actually shared thing work? So you could actually have a function called f that returns a value, right? I have a function called g that returns a value, and I go ahead and execute that. So f might be scheduled on a node 2, and then it returns an x, so it's going to store the value of x as a reference in that particular shared memory, and then it returns me IDX right away. I have another function called g, which actually depends on the value of function x, but I don't send the value of x, I'm sending it an object, right? And because it knows the locality of the particular object x, it's going to schedule that on the same node, so I don't have to copy across node. And that way, it'll just get the values read from x, compute y, and then return in ID y. And then you can just do a get on that. So that was, in a nutshell, very quickly, the 3 APIs that we're going to work on. Any questions? OK, how many of you actually have set up your computer with this? OK. So this URL, RayServe tutorial M class, just at home, just do a pip install, because I don't want you to do a pip install. It's going to take a long time. It'll break. We'll be here till happy hour, and I don't want you to be standing here between you and the happy hour. OK, so that's it. Now let's look at some code. Can you guys see? Okay, so the first lab or the first tutorial is very simple. I'm going to talk about how you can actually do distributed computing using the remote functions, right? So normally you're going to take a function and convert that into a task or convert that into a remote setting. So we normally do a very simple thing. We import our statements, and then there is a difference between task parallel and task serial. And the way you actually define something to run on Ray is by just giving a particular decorator, and then you don't have to worry about where it's going to be scheduled or whom is going to schedule or whom should you tell it to schedule. It will do it automatically for you. You just deal with your Python code that you're actually used to. So it's very Pythonic, right? You're not worrying about it. You're not creating a socket, and you're not connecting your particular socket, and you're not serializing your data, and you don't have to worry about any of those things. That makes the beauty of Ray, which is very, very simple for you to actually convert your existing functions into a remote setting. So this very simple function, we'll get into some more complicated stuff. So regular function, all I'm doing is I'm just returning a value. Remote function, all I'm doing is just putting a decorator. Now this is going to be a remote function. And then when I invoke those two, I'll just do this, and I'll initialize Ray. And there is a static function called isInitialize. If it's initialized, I want to shut it down because I want to start everything anew. And then I can just say Ray init, logging level is whatever it is. And there are other parameters you can actually specify. For example, I can say how many CPUs do I want this particular array to be initially. If I have 12 CPUs by default, if I don't specify how many number of CPUs, it will create 12 workers for me on my local host, and each of those will be tied to a particular core that I have, right? And I can provide other environments over here. If I just want my runtime environment for this particular instance array to have additional packages which are dependent, I can provide a runtime environment. If I have some files that are sitting on my directory that I need to be uploaded, I can actually provide, as part of my runtime environment, it would actually upload it to the cluster. So we go ahead and create this particular array, and it returns a cluster. I'm a context, and the context is just another dictionary that, I'm not going to the next local, yeah. It just prints out what it is. And it creates a little dashboard for you, so you can actually look at the particular dashboard. And if I click on the dashboard, you might actually see what I mean by that. All right, so now we're just going to go ahead and invoke this particular function. See, it came right away, and what did it return me? It returned me this massive object reference, which is just an ID. Right? This object reference ID can be something that you can actually refer to as a feature that you can actually inquire to say, what's the value for that? So I do array.get on it, and I get the value back, right? And if I wanted to iteratively do that, I can, no parallelism, I create this particular compression list, and I send in 10 values, and I don't assert I should get 10 values back. And I can do the same thing with parallelism. The only difference over here is I'm just invoking with the remote function, and then once I'm done, I just get that particular list, and I can just send the list of references to do get, and it's going to get all those values. So these two are identical in its format. Okay? As simple as that. No sockets involved, nothing. I didn't have to worry about it. All that is actually done automatically for me. So let's look at this particular example that we talked about in the book, in the slides, where I have two. I have a function called readArray that takes in name of a file, and it just reads and then it returns me a numpy array. So we'll create this particular function, and then we'll define another function that takes adds those two arrays. I create two numpy arrays, return the value of add. And what we're going to do is we're going to sum now all the contents of that particular array, given a particular array, and then we're going to return it. Very simple, but these arrays could be huge. This could be massive tensors that you're actually working on. This could be something that you might be doing in your grade computation, but I just want to give you an idea, an illustration of how simple it is for you to be able to do that. So we go ahead and now read a particular array by providing a path, and I get my object reference back right away. It didn't wait for, it's happening now in the background, but I can always get that value. I'm going to read another one, and I'm just going to go ahead and send the references to this, right? And then what I get back is a reference again, obviously, and I'm going to fetch the result. And I fetch the result, I get the contents of that particular two arrays added together. And I can do the same thing. I get the sum of these arrays, Again, I'm sending the reference. I'm not sending the array, I'm just sending an object reference. And it's a lot easier to serialize rather than sending an entire array because it's sitting on my object store and it just resolves that and use those values. And now I get the sum of those arrays. So that's very simple, right? I pretty much wrote this distributed way to distribute my computing. Right now, running on my 12 cores. Why is this not running? Okay, see, I got my 12 cores over here, and all those could be utilized for any of these, and we'll see how those are going to be used momentarily. Okay, so let's do something more complicated fun. Let's create a Fibonacci series, which will involve, obviously, a little bit of computation, and that way it may actually, so we'll generate a local function called Fibonacci, and we'll create a remote function that just wraps the local function around. We'll count what number of CPUs we have. We got 12. So I'm going to create a local instance of that by running this in a comprehension list. And then I'm going to time what my local takes me, right? So I'm going to run that. And if you look at, so it took about 4 seconds to do that. I'm going to convert now my remote function, which is nothing but using the Fibonacci remote, and return the results. And if I run that, that took less than 1,000 milliseconds, right? Very quickly because it distributed the task. Now, when you actually have larger tasks, you will see the huge benefits of that. Let's look at some of the other patterns that are quite common. Let's say you actually have a massive array where you actually want to compute the sums. Now, depending on how you schedule the tasks, if the tasks are taking the first one and then computing it with the second one and the third one, you actually have a skew. But if you rearrange the way you're going to add the numbers, you actually get quite a shorter version of it. So let's see how we can actually do that. So that's just my remote function called add. And I'm going to create a range of values, and this could be 1 million values. You never know, but I'm just creating a short value. And then we just iterate the loop. Now, the first one over here is using the first method. And if you look at what's it actually doing is it's doing the first one, it computes the object, it returns the object reference, then it's going to compute the second one, then it's going to compute the third one, which returns an object reference. So you actually are doing it in a more inefficient manner. You can actually say it took about 7 seconds. If you change the values slightly and you arrange the way you actually do these, this might be a little faster, right? I run that and it took less than 725 milliseconds. Right, because the way I actually arrange those adds, so it would compute those two references, add them together, use references, add them together, and then finally I get the value back. And then when you want to shut down your cluster, you just do a shutdown, and these 12 cores which are running will disappear. Now I have exercises over here, and obviously some of you haven't installed, so it would be unfair for you to do that right now, but please take this at home. If you suffer from insomnia, this would definitely put you in coma. Good way to entertain yourself tonight, especially after the happy hour. And then for homework, try the bubble sort, right? I did a Fibonacci, take bubble sort and see if you can actually do both a local version and distributed version and see how it is. Try to increase the number of Fibonacci numbers and compare the times it actually takes. So when you go beyond 300K, you will actually see your local host going, right, locally. But if you actually run it over distributed, it will, and when you look at the array dashboard, you'll actually see all the Fibonacci runnings on each and every cluster. And there's some references over here for you to peruse through. And I have sort of a more 4-hour tutorial called Array Core Introduction. You can actually it's on YouTube. You can actually look at that. Okay, so that was the first pattern that we talked about, Array Core, and I have to move on fast. Let's go to the second one. Right? The second one is the object store, which is a guided tour of how you actually use this object store. And there's a certain protocol that is actually used in how objects are resolved, right? There are two ways where the object store works. One is it uses an in-memory store if the object store is less than 100 kilobytes, I believe. Could be wrong, but I'll check. And the other one, if it's more than that, then it will actually use the shared memory. And if it's a small object, then we just use the in-memory store and we just copy it over. So there isn't that much of overhead. But if it's sitting on an object store, then we just put it in object store and we just pass the reference, and then the same task which is running on the same node can just get directly using zero copy. So here we are. We're going to do the same thing again. Object my reference. All I have is I'm just creating a num list of the way you actually put things on the object store. You do ray.put and ray.get. Simple as that. 2 APIs, right? It doesn't matter what your object structure is. It could be a pi-arrow dictionary. It could be a pi-arrow data structure. It could be a numpy. It could be a tensor. We'll convert that and serialize. If it's an arrow object, it will use the arrow serialization. If it's a Python object, it's going to use picklefy to serialize and put it in the object store. And obviously, when you do a put, it's not going to return the value. It's going to return your reference to that. And same thing when you want to get, you just do that, and it'll return you the value back. Same thing, remote function now takes a list and then returns your sum. I can do the same thing, calculate the sum for object reference, and I get the result back, right? Very simple. And if you actually want to somehow use comprehension in using that, it's very easy. You can just put it in a particular loop, and then always surround your last function with the get. If you put get within that, what will happen is that you'll block every time you're doing a put, right? But if you just do a get at the last time, you just get all the object references and get that immediately. So let's look at some example. What about if you have a task that's going to take a long time? Let's try to simulate something that's going to long time, right? Let's say you're doing computing for a long time and it's going to sleep for 6 hours or 6 minutes or 6 seconds, whatever it is. And you want to make sure that you don't wait for that long, right? And so when you're doing a get, you can actually provide a timeout whereby after that particular value is exhausted or expired, it will return back and create an exception, and that way you can actually go and do other things. So this would be one way to say, if I'm doing a get on an object and it's taking too long, and I don't really want to wait for that, so I'm just going to create an exception and do something else. What you do something else, obviously, is depending on use case. So that's a very easy way to take your objects and put it in the object store. If you have models, for example, IBM uses the object store to put the massive large language models, and then RayServe can actually just fetch that directly, so they don't have to worry about putting it on the cloud. So Ray shutdown. The final pattern that I want to go before we actually I hand it over to Archit is the Ray core design pattern called remote classes. And I think remote classes is very, very important for you to really get a good grasp, because it is really the basis in how all the other libraries are done, right? How the design pattern is actually used quite a bit. And the way the Ray let schedule those things is it detects a particular class and then converts that into schedule this to a particular worker. So your class will always run on one worker, right? And so you're always dedicated to make sure that particular worker is running on that. And so you don't have to worry about synchronizing. You'll always have one entry point for that particular worker. So let's do a very typical pattern that you actually see quite a bit in machine learning called parameter server. What we do is we'll try to implement this parameter server where we actually have a worker which is computing gradients, and then is going to compute gradients and return it back to the parameter server. The parameter server keeps track of all the workers who are computing all the gradients on that particular server. This is a very common pattern used in distributed computing, where the synchronization of gradients are done in a distributed manner, and they somehow sync up that before Nickel and all the other protocols were invented. So parameter server is very simple. I have a class. And I've made that into a remote class because I wanted to maintain a particular state. I get my initial parameters. I'm just going to assign it to 0. And then I have a function called get parameters. Now, the get and set parameters, we don't support the property value right now in remote functions. So you actually have to have an explicit get to get the value of your local variables. And then update parameters just gets a gradient and then updates that. And so it keeps state of that gradient. And now I'm going to create a worker. And each worker is going to run for about 25 iterations. It'll sleep for a certain time, assuming that it's doing some weight. And then I'm going to initialize that, each one with 10. And then I'm going to update those gradients randomly. So we're going to create those workers. I'm going to create this parameter server. And now I actually created an actor. So now I actually have an actor, which is a parameter server. And what I'm going to do over here is initially set the parameters value to start with 0. So now I have a parameter server which is running as a stateful service. In one of the core, it returns me 4 workers. So I'm going to go ahead and create now 4 workers, so 3 workers that I want it to run in parallel to compute the gradients. And then I'm going to launch these workers to update my gradients as they go along, right? So it's very simple. Send the value of that particular remote function, call the parameter server.getRemote, and now I'm actually computing the gradients as it goes along, right? So this is now actually happening in the background. It's actually creating the gradients, upgrading, and at some point it's going to go ahead and stop running. And if I see that in my dashboard, I should actually see the parameter serving is probably done by now. And the last, before I hand it over, is this very pattern that's very common using classes in Ray libraries. Ray training, Ray serve, Ray hyperparameter tuning use this design pattern where you actually have the driver just submits a supervisor actor, and the supervisor is the one who actually creates these workers. And the workers can do your distributed training, or they can do distributed hyperparameter tuning for each and every trial, and then returns the results back, just like the parameter server, you return results back to the main supervisor, and the supervisor decides, oh, is this worker really worth doing hyperparameter tuning? It's not, I'm just going to chuck it and then move on to something else. So this design pattern is very common in almost all the native libraries, and a lot of people actually use that. So here we'll try to simulate by having a particular model that does training, and then we have a factory model that's going to create 3 different kinds of model, right? We can actually have a model called a reinforcement learning. I mean, we can create a model called linear regression or cat boost or XGBoost. So this is just a toy example, but these is how we actually do that. We have states that's going to define, and we create a remote worker that takes in any of the model that it actually has, and it maintains this particular state by figuring out whether it's actually doing training, and then it's going to do the work. And the work is about creating a model factory and then invoking its train function to go ahead and do the train. So this is actually happening now in a distributed manner across the cluster. So we're going to create a supervisor over here, and all the supervisor does initializes my set of workers, right? I need 4 workers, 3 workers with each of these different kinds of models, and I'm going to create those particular models. And then I'm going to launch those particular workers, and then I can either terminate or I can actually find out what the state is. So this is your supervisor that's actually running and keeping state of where things are. And once it's done, it's going to go ahead and kill them. So I start my supervisor. I get an object reference to it. And then I'm going to go ahead and do my worker. And you can actually see over here, this should be running. So this is actually running, and it's done, right? So that pretty much sort of gives you an idea of how you can actually write very simple distributed computing you have done there, right? You created 3 workers. You created a supervisor. You just wrote a function called remote. You just wrote a function called compute gradients. You just wrote a function called update the state. You didn't have to worry about creating a socket. You didn't have to worry about where it's actually running. All that is actually taken care of. You, as a Python programmer, just write the simple APIs, and Ray actually takes care of that underneath for you. That's a huge, huge improvement. Think of it, right? Those of you who actually come from distributed computing background, who actually were writing C and C++ code, programming HPC or using MPIs, can attest that this is an astronomical advancement in how you can actually write simple APIs. It's all Pythonic, right? There's nothing new about this, right? You're just using the same design patterns that Python allows you to do that. decorators is a Python package. Remote is the only thing we have added, but that remote is hidden for you. All you do is just create a remote, and Ray will take care of the underneath thing here. So I think in the interest of time, I want to end over here. There's this other thing called message. Run through it. There's an exercise at the end. I advise you to do it. There's a solution. Don't look at the solutions, but this will sort of give you can actually write these actors and these distributed actors in a very, very simple manner. And normally when we conduct this particular sessions, it's normally like a 4-hour class, and I normally break for about 5-10 minutes, so you guys can do the exercises. But today, given the state of things, and we only have half an hour, 1.5 hour, I'll make those optional. But we will hang around here at 4:30 afterwards if you don't want to go to the happy hour and write some code. We are here, definitely. So it'll be fun to do the exercises if you actually have it set up. So I'll have Archit come in and do the second part, which is how you actually write, how you deploy models using RayServe, which is the second library. And the reason we had to set the context for you so you understand what's actually happening when you create a class and use a decorator called serve deployment. So Archit, here you go.
Okay, yeah, so thanks, Jules, for telling us about Ray in general and some of the core pieces of Ray, like tasks and actors. So I'm going to dive into one of the libraries built on top of Ray, which is RayServe, specifically for serving machine learning models, or really serving anything. So as a sort of a summary, what is RayServe? It's a scalable and programmable serving framework built on top of Ray. And some of its key features are that it's framework agnostic, so you can use it with any framework you want. It's not like locked into TensorFlow or PyTorch or anything like that. It's Python first, and it's easy to use. And we're going to see some code examples and go through some notebooks that show you how simple the API is. So here are two really basic code snippets. You don't even really have to read these. We'll see these in the notebooks, and you'll be able to run them. But on the left, we have sort of the most basic RayServe application. So at the top, we're importing the serve library. We're calling serve.start, which starts the Ray cluster either on your local machine, or it can connect to a Ray cluster on a remote cluster. And then we have this serve deployment, and it's just sort of a hello world deployment. And you can see it takes in a request, and that request is a Starlet request object if you've used the Starlet web framework before. And at the end there on line 9, we're just deploying the deployment. And on the right, you can see how you would sort of query it as a web service. So here we're just using the requests package, and we pass in the parameter serve as the name, and then we get the response, hello serve. So let's talk about some things that are specific to machine learning. So one of these things is being able to use GPUs for model serving. A lot of machine learning models depend on GPUs. And you can see here in the serve.deployment decorator, we've passed in num GPUs equals 1 as an option. So every replica of this deployment, whether it be one replica or hundreds of replicas, each one is going to be allocated 1 GPU. And you can even specify fractional GPUs. If a single model doesn't saturate a full GPU, you could put like 0.1 or 0.2 or whatever you want there. Batching is another machine learning specific feature that can be helpful. So it may be the case that for your model, if you want to do 10 requests at once, it's actually it's faster than if you were to just do 10 requests individually. You can do them in one batch. So RayServe will support that as well, using the serve.batch decorator. Scaling out, you can see we've specified num replicas equals 10. That's actually all you have to do to specify how many replicas you want. And serve is built on top of Ray, right? So under the hood, it's using Ray actors and tasks. And we'll see a little bit about that in the architecture in a following slide. But as a user of RayServe, you don't have to think about actors and tasks. You just specify, I want 10 replicas, and Ray will manage scheduling those replicas on different nodes, different CPUs. And then finally, model composition. And we're going to talk a lot more about this in this presentation, but in applications, you're not just going to use one ML model typically. You might need to chain them or have an ensemble. There's a few different patterns that we'll see, which will allow you to hook up your different models to each other for your full application. This other line, which I didn't talk about, line 7, load model from registry. Every time you make a request, you're not going to load the model. Instead, you have this stateful class. Once it's instantiated, you can load your model, which might take a while. But then once it's loaded, it'll serve the requests fast. OK, so here's a very general graph, maybe kind of ridiculous, but we're just trying to say here that RayServe combines both the ease of development, so a Pythonic API, which we'll see, and a native fast API integration, which we'll also see, together with the high performance and scalability which comes from being built on top of Ray. So yeah, like we said, some of these machine learning applications, it may be harder with other frameworks to scale up, and less Pythonic. You might have to fiddle with YAML files and things like that, or you might be locked into a specific framework. And with RayServe, it's framework agnostic, so you can use it with whatever other tools you're using. So just as kind of a summary, we already talked about composing models together and scaling out a single model. RayServe also will let you update your models over time, right? In real life, you are going to improve your models over time, and so RayServe will let you version your deployments and update them in production. So we talked about model composition. I'm sure all of you are probably more familiar with all this than I am. There's 4 ones that we're going to talk about here. And it's pretty, the pictures sort of say a great deal about what they are. So pipeline, ensemble, business logic, and online learning, where your model is learning from the environment. For the sake of time, we'll dive into just 2 of these, just the pipeline and the business logic, and see what they look like in code with RayServe. So we can start with the pipeline. It's just a chain of models where the output of each model will be the input for the next model. And here's sort of a concrete example of what this might look like. So here we have all these different types of models, like a detection classifier, detecting some key points on this cat, and then like a natural language processing model at the end. So this just illustrates one example of chaining models together. So now let's look at 2 implementations that are, if you're not using RayServe, you might just be using like a typical web server here. Here you're loading the model every time the request hits this endpoint. On the right-hand side, you have an example of, I guess, managing some YAML using some other framework. With RayServe, and again, you don't have to read all this code. We'll see it in the notebook. But the main point here is we have 3 deployments here, the featureizer, which we've omitted the code, and the predictor, and then some other deployment called orchestrator. And we're just calling the other deployments from our deployment using pure Python. So we get the handles to these other deployments in the constructor. And here you can see we feed in the input, get a feature, you feed the feature into some other deployment, you get the prediction, and then finally you return the prediction. This is the same code on the left as before. And this is what it looks like on the Ray cluster. So this is just if you're curious about what's going on under the hood. These are all actually Ray actors, these little boxes. So this is the serve controller, which manages the state of RayServe and all of the replicas for each deployment. This is the HTTP proxy actor, which actually receives the requests. You can set RayServe to have one of these actors on every node and then have a load balancer on top. Or in this example, just have one on, for example, the Ray head node or whatever node you like. And then these 3 deployments, they're just 3 boxes here. However, each one can be scaled individually and have multiple replicas, depending on which one is receiving more load. But here we just have one. And these arrows represent the calls in Python. So just a summary, the Pythonic API, high performance calls, gRPC, and one line to scale to however many machines, CPUs you want We just saw that num replicas parameter in the constructor. We'll see it again in the notebooks. Ensemble, we're going to skip over. You can sort of imagine how it looks. One thing I'll say about Ensemble, because this is all pure Python, you can define rules like having the output of one model decide which model to call next and things like that. You don't have to have a static sort of graph, inference graph, right? You can just do whatever you want in pure Python. And that's sort of similar to what I'm going to talk about for the business logic here. What is business logic? That's a quote from Toy Story. So database lookup, web API calls, feature store lookup, anything that's happening outside of the ML inference, but you still need it for your end-to-end application. We'll just call that business logic. And because it's in pure Python, you can just sort of write it in Python. So what is this code sample? It's a example diff of if you were starting out before RayServe and then you're upgrading to RayServe, what kind of differences in the code would you have? So maybe you're using like a fast API type web framework. You just replace the decorator with the serve.deployment decorator. Here, instead of loading the model here, you could have a model in a different deployment and scale that up independently, right? Same thing for the model inference. So the point here is by using a distributed Ray cluster, you can offload the compute-intensive, memory-intensive tasks to other processes or other nodes, even physical machines on the cluster. So arbitrary business logic, like I said, separate the compute-heavy work. A native fast API integration, which you can see in our documentation, and we also have a notebook about that, which makes it easy to move from your existing fast API application. And then, yeah, it lets you scale out easily to however many replicas you want for each model. So sort of the final summary, because RayServe is built on top of Ray, it gives you these benefits like efficiency, low latency, and so on. Because it's pure Python, you can define arbitrarily complex deployment graphs, just define them in the code, and you'll be able to mix your business logic and your machine learning inference. So before we go into the tutorial, any questions for me or Jules? Yeah.
So you're talking about how you can scale things up as part of this.
Mm-hmm.
Does that happen automatically, or is that something like that I have to react to?
Yeah. So we actually do have an experimental auto-scaling feature. And the way that works is it'll set the number of replicas based on the queue size, so how many requests are piled up waiting at each node. And there's some parameters you can configure there. So we're very eager to have more users try that out. Apart from that, though, you would just be setting manually the number of replicas. So feel free to ask more questions as you think of them as we move through these notebooks. Let me just find the notebook. Okay, so yeah, we're going to be on exercise 4, if in case. Oh, is it? Yeah, it's kind of small, huh? Okay. Maybe one more. Yeah, so a bunch of stuff that I talked about in the presentation. Let's skip to the code. Okay, so let's initialize Ray. So if you're just using Ray like by itself, you would use ray.init. Here, RayServe serve.start automatically calls ray.init. So now let's create the simple deployment that we saw in the first slide. And now let's talk about what all the different lines of code mean. So serve.deployment is just a decorator that you use on top of any serve deployment. And what is a deployment? You can think of it as one model which you might scale horizontally to any number of replicas. So this is pretty simple. We've seen it before, but let me run this cell. And how do you deploy it? It's just hello.deploy. Okay, and then, I don't know if we can see both of these at the same time. Yeah, let's just run this code from that slide. So we're just going to use the requests library to query this deployment over HTTP. So RayServe has a UVcorn server built in so that this just works automatically, but you can also hook it up to an existing web server if you're using that. Yeah, so we requested it 10 times. So that was a function, right? Now let's try serving a stateful class. So what is this class doing? We have some attributes here, which we can update. We've defined a predict function that will return our sort of fake prediction. And then finally, this call method is what's automatically going to be called when we query this deployment over HTTP. So that's going to parse the query parameter out of the starlet request and pass it to this method that we defined. So let me run this and then deploy it. Are there any questions about what this code is doing? The reason we've split it across a call method and a predict method is that we can query the model in two different ways. You can either query them directly over HTTP or from Python. I guess we'll see that later in this notebook. Here we'll just do it over HTTP. So this is on localhost /simple model. You can configure the route. Yeah, go ahead. This one? Oh, I see. This one. So this is if you're developing locally and you want to test it out. I guess it'll automatically print out which URL to use. So that's just what we put over there. Yeah. Other questions? Yeah. So I should say one other feature of RayServe is that you can run your entire RayServe locally before pushing it to production and like jacking up the number of replicas and all that. And you can do the same for any Ray application. You can just run it locally using the different CPUs on your laptop, and then later run it on a cluster with the same code. Here's another useful API, list deployments. These are just the two models that we had. There's a version field. If we ever update the models, this version will get updated automatically, but you can also manually set a version, things like that. Route prefix is also customizable. It just defaults to the class name or function name. Okay, so machine learning models, this example will be slightly more in depth. So this is an example of a model that you maybe have saved or maybe is in some model registry or something like that. Maybe an MLflow model registry or something like that. And here is the serve deployment. So in the constructor, we'll pass in, well, okay, this path variable doesn't do anything. It's just as an example, but you can imagine how this would look in practice. And we're also just going to record the process ID just to print it out so we can see that there's different replicas running in different processes. So let me actually run this. And then as before, we have the predict method and the call method to handle HTTP. So what we're going to do now is to illustrate how you could use the same class and have different deployments with different parameters. Here we're just giving them different names and different, let's pretend this is a pickled model file, right? Model 1 and model 2. Run this. And we've deployed both of these. And you can see that they're both ready. Let's see list deployments again. Yep, they're both there. We still have these old deployments lying around. Yeah?
So are each of these deployments using different HTTP servers or just one server?
Just one server, yeah. That's right, yeah. Yeah, that's right. Yeah. So yeah, different routes, but it's the same HTTP server. Yeah. Okay, now so yeah, this is what I was talking about before. I was getting a little ahead of myself. So here, there's two methods for actually accessing these deployments. One, which we already saw, was over HTTP, and we used the requests library. You can also do it within the Python code, and that's what we sort of saw in the slides with the get handle, or get deployment. So what is this code doing? Well, for each of these deployments, you call serve.getDeployment. You can pass in the name, and you'll get a handle to that deployment. And then to get the prediction in Python, you call handle.predict.remote. And like Jules was saying, this returns a future. So to block on the result of that future, you call ray.get. You wrap it in ray.get. And then that'll evaluate to some value. So let's run this. Okay, so we queried the deployments, and you can see that the PIDs are different here. And the second way that we saw before is to do it over HTTP. This looks pretty similar to what we had before. And we'll just finish by shutting down reserve. There's some logs. It's shutting down the replicas. And exercises for you to do whenever you want. But we have one more notebook that I do want to get to. Any questions about what we saw so far? Yeah. So the Python calls, sorry, are they? Oh, no. It's just like a call between Ray actors, so gRPC, yeah. So it's not going through HTTP, yeah. Yeah, I think so, yeah. Yeah, that's actually why we have it sort of separated here. So the Python call actually directly just calls this as a Ray actor method. That's sort of the details under the hood. Other questions? Okay, here's kind of a fun example of model composition. We're going to do some kind of sentiment analysis. I think I have this installed, so this should be fine. Let's see. Yeah, it's already satisfied. But I'm just installing some dependencies. Hugging Face transformers is what we're going to use, and torch. Okay, so these are some tweets, I think maybe written by hand by Jules, or these are Jules' actual opinions on dogs. There's multiple personalities there. So let's just load them into tweets. Did it run? Okay, and then, we're pretending that this is the Twitter API. So now we want to analyze these. So let's look at the actual serve model here. We're just setting num replicas equals 1 here, but it's a very compute-intensive model. If you had a cluster and you wanted to serve lots and lots of requests, you could increase this, and then it would be scaled horizontally. And all this is doing, this is just some standard stuff for when you're using this library. But it'll tell you whether the tweet is like positive or negative in sentiment. So that's a serve deployment, the sentiment model. And then we're going to do another model which translates it. I'll just run this. So we're going to take both the sentiment and the translation and compose them by using this third deployment. So here we got the handles to the two other deployments that we had, the translator and the sentiment analysis. So what does this function do? It grabs the data, calculates the sentiment and the score. So we're really just concatenating the output of these two different models. But you could imagine doing something more complicated.
It gets a translation as well.
Yes, the sentiment score and the translation. So now let's start serve, and if I remembered to run all the cells, we'll see some output here once we deploy the three models. Okay, is that all of them? Compose, translate, sentiment, yeah. Okay, so now let's just send in some tweets and okay, some warnings. All right, we got some output. Yeah. All right, so any questions about this notebook? Let me just, well, I'll let it finish, but questions?